Hello everyone, my name is Kyeremateng-Boateng and I'm presenting this research paper on the topic Prediction of Radio Frequency Spectrum Occupancy, which is a joint research with authors Marvin Kuhn, Dasana Joshola, Manohar Mariboyana. So I'll be presenting the introduction and then I'll give some background information and then some methodology, and then I will go into our results and conclusions, and then I'll give our contact information. So if there's any question that you want to send to the authors, you can send to our email and we will respond as soon as possible. Increase in wireless users has resulted in limited availability of spectrum resources. Dynamic spectrum access allows adapting to changes in spectrum bandwidth occupancy by predicting future spectrum states. DSA enables licensed and unlicensed users to share the same spectrum bandwidth by preventing collisions between users. A time series method can be used for DSA by monitoring the temporal busy or idle states of each spectrum channel. Background information. Energy detection. Energy detection detects primary users' activity based on the energy of the signal received. Using this energy calculation, where M is the number of samples and YRFM is the observed complex radio frequency signal at time M, and RFM is the magnitude and its scalar quantity. Energy detection is one of the techniques used in this research for detecting spectrum occupancy. Cumulants. The cumulants Kr are the coefficients in the Taylor expansion of the cumulant generating function about the origin. The rth moment of a real valued random variable x with density fx is given by this formula. The first order cumulant is the mean, the second order cumulant is the variance, third order cumulant is the skewness, and fourth order cumulant is the kurtosis. First order cumulants of the raw signal was the second technique used in this research to determine the spectrum occupancy. Support vector machine. Support vector machine is a supervised machine learning method for classification that finds a hyperplane that maximally separates the different classes in the training set. Support vector regression (SVR) is an extension of SVM and is used as a regression model to predict real values rather than class membership. Reactive prediction. Time series forecasting methods allow for predicting future data states based on observed data states. As an example, at time t, one can predict yt plus 1, yt plus 2 to yt plus n, where t is the forecast origin and n is forecast horizon. Reactive prediction uses a one-step look-ahead method to project the value of the current state to the next state. Methodology. Generating RF data. We simulated the RF data with idle and busy activity statistics, which follow a Poisson distribution. Mix various levels of white Gaussian noise to generate RF signals with different SNRs. The activity statistics defined as lambda 1 and lambda 2 ranges from 0.1 to 0.9. The SNR levels ranges from 20 dBm, 10 dBm, 0 dBm, negative 5 dBm, and negative 10 dBm. The generated data is split evenly between training and test set. Size of training and test set is given by this formula where D is the number of samples in each state, which equals 100, and N is the sample size. Baseline reactive prediction. The baseline reactive prediction assumes that the current occupancy state is known. It projects the next occupancy state will be the same as the current state. This results in an error for each state transition because it assumes that the current state of a signal remains constant into the next transition. Conventional energy detection. Conventional energy detection operates without prior knowledge of the primary signal parameters. Total number of sliding windows is given by ms equals d times n minus 1 plus 1, where d is the number of samples in each state, which equals 100, and n is the number of states, which equals 1000. For each sliding window m, energy values are computed using the following equation, where YRF K denotes the magnitude of the observed RF signal and its scalar quantity. A threshold value lambda ED is used to determine if a signal is on or off, which also means which is present or absent. The threshold value for energy is calculated by this equation, where D is the number of samples in each state, which equals 100. PFA is the probability of false alarm. Q minus 1 is the Q inverse function, and the noise variance. So if ED is greater or equal to lambda ED, then it means that a signal is present or there's a presence of a primary user. If ED, which is the energy, is less than lambda ED, it means that a signal is absent or a primary user is not present. First order cumulant. The first order cumulant of the generated radio frequencies are calculated using this formula. So YRFK denotes the magnitude of the observed RF signal and it's a scalar quantity. The threshold value for the cumulant of first order is given by this equation, which is equivalent to the square root of the threshold of the energy detection. The occupancy state is determined by comparing the value of each state with the threshold value. So if CD, which is the generated cumulant value, is greater than or equal to the threshold value lambda CD, then a signal is present. If CD is less than lambda CD, then it means a signal is absent. Reactive prediction using energy and cumulant. Reactive prediction predicts the next state of the signal using the current signal occupancy state. The energy and cumulant of the present state are thresholded with the threshold value lambda D, and for energy is lambda ED and cumulant is lambda CD to get the observed state vector. The current state K is compared with the next state K plus 1 in the occupancy state vector. Linear SVR prediction model. For each of the model, a training sample size of 1000, an SNR value of 20 dBm, and activity statistic of 0.9 for both lambda 1 and lambda 2 were used to train the SVR model. In both energy and cumulant prediction, the predicted values are compared against the observed state to determine the accuracy of the prediction. Below are the parameters that were used to train the SVR model. So the results. Baseline reactive detection results. From our research, it shows that as the activity statistic of a signal increases, the detection accuracy decreases. So in this diagram, you will see that the activity statistic was 0.1 and the detection accuracy was 0.9. But as the activity statistic increases to 0.9, the accuracy decreases significantly for all SNRs. Reactive detection. Reactive detection for both energy and cumulant showed that the accuracy for SNRs between 0 and 20 showed better accuracy detection than the SNRs of -5 and 10, which was for both energy and cumulant. Conventional detection results. For both energy and cumulant, the conventional energy detection showed that for SNRs of 0, 10, and 20, the accuracy starts off at approximately 0.9 and then degrades as the activity statistic increases. But it also showed that for SNRs of -5 and 10, the accuracy doesn't perform very well. It starts off a little above 0.5 for -5 dBm and then degrades as the activity statistic increases. But for the cumulant, the SNR of 0 starts off at around 0.85% and then degrades as the activity statistic increases. Predictive prediction results. Using the SVR model that we trained for energy and cumulant, we were able to get much better results in predicting the state of a signal as compared to conventional detection and also reactive prediction. From these two diagrams, you could see that the accuracy for SNRs 10 and 20 are very high even when the activity statistic increases. In the energy prediction, as the activity statistic increases for dBn for SNR 10 or 20, the accuracies also increases. But then for SNR of -5 and -10, as the activity statistic increases, the accuracy also degrades. Similar to the energy, the cumulant prediction also have much stable accuracies for SNRs of 10 and 20, but then for SNRs of -5 and 10, the accuracy degrades as the activity statistic increases. For both predictions, the SNR of 0 degrades as the activity statistic increases, but then it started off at a higher accuracies and then the prediction degrades as the activity statistic increases. Conclusion. We compare three methods of predicting signal spectrum, that is reactive, energy detection, and first order cumulant. We analyze which method performed better at various levels of SNRs and also signal activity. Higher SNR levels performed better at predicting signal state for all three methods, although the accuracy decreases as the activity statistic of the signal increases. At lower SNR levels from -10 to -5 dBm, prediction accuracy significantly degrades. Overall, using high SNR levels, the SVR predictive techniques showed significant improvement over the reactive predictive techniques. And here is our contact information. If you have any questions about this PowerPoint or about our research paper, you could send us an email and we would respond as soon as possible. Thank you very much. Goodbye.